Welcome to AI Paper Podcasts. Today we're breaking down Fast-ThinkAct, efficient vision-language action reasoning via verbalizable latent planning.
This one comes from a team at NVIDIA, National Taiwan University, and UIUC.
And it really targets, I think, the biggest problem in embodied AI right now, which is just how slow these reasoning models are.
It's that classic trade-off, isn't it? You can have a robot that's fast, but, kind of dumb.
Right.
Or you get a really smart robot that has to pause for 5 seconds to think before it picks up a cup. This paper really claims to have found a way to get both.
And the numbers they're reporting are, frankly, pretty wild. They're talking about an 89.3% reduction in inference latency compared to models like ThinkAct.
Which is state-of-the-art, and they do it by compressing this long text-based chain-of-thought reasoning into, well, they call them verbalizable latent vectors.
So instead of hundreds of words, it's just a few compact ideas.
Exactly. And the upshot is that robots can reason in real time at something like 1 to 15 hertz instead of the 0.1 hertz we're used to, which is basically a slideshow.
A massive step, then, for actually getting these things out of the lab and into the real world. Okay, so that's the high level. Let's tear into how it actually works.
Sounds good.
To really get why this paper is so important, you have to look at the landscape of these vision-language action models, or VLAs. It feels like there are two camps.
There really are. On one side, you have your foundation VLAs, so things like OpenVLA or PyBaller.
Okay.
And these are what you might call System 1 thinkers. They're fast, they're intuitive, it's all imitation learning, pixels in, actions out.
So it's like pure muscle memory.
That's the perfect analogy. They're great for a task they've seen a million times, but, you change one little thing in the environment or you give it a long horizon task and they just fall apart.
Because they're not really planning?
No, just matching patterns.
Right.
That's where the other camp comes in, the reasoning VLAs, ThinkAct, MomoAct. These are System 2 models.
This is where the robot literally types out its thought process.
Yeah.
First, I will identify the red block, then I will move my gripper towards it.
Right. It uses chain of thought to generate this whole text plan before it acts, and it works. I mean, the performance boost is huge.
But the cost is that latency we talked about.
An enormous cost. Generating that reasoning trace can take, 250 text tokens?
Yeah.
On a normal GPU, that's seconds. And a robot just can't afford to be a statue for 5 seconds every time it needs to make a decision.
So Fast-ThinkAct wants the System 2 intelligence, but at System 1 speed. How on earth do they compress that reasoning without losing the actual the reasoning?
Well, the core idea is shifting from generating explicit text to what they call verbalizable latent planning.
Okay, let's unpack that.
So instead of forcing the model to pick from a vocabulary of, say, 50,000 discrete English words, the model in this paper, the student model, it just outputs a short sequence of continuous latent vectors.
So for the engineers listening, that means it's outputting the raw, dense embedding, not a specific token ID.
Precisely. Think about it. Human language is kind of inefficient for describing physics. You might need 20 words to describe a tiny course correction.
All right.
But in a high-dimensional vector space, you can encode all of that intent and dynamics into just a few numbers.
And the compression they mention it's huge. The teacher model generates 250 text tokens. The student generates, what was it?
6 vectors.
6 vectors versus 250 words.
Yeah.
I mean, that alone explains the speed up.
It does, but it also creates a massive new problem. Alignment. How do you make sure those 6 numbers actually mean something and aren't just, noise that's overfit to one specific task?
Usually you'd supervise it with a ground truth text, but you've taken the text away, so what's the guide?
This is the verbalizable part, and it's really clever. They set up a teacher-student framework. The teacher is a big VLM that generates the slow, verbose reasoning. The student learns to copy that reasoning, but in its compressed latent space.
Okay.
To keep the student honest, they add a special component called the verbalizer.
The verbalizer.
It's basically a decoder that's bolted onto the student model, but, and this is the key, it's mostly just used during training.
So it's like a sanity check.
It's more like a semantic tether. Its whole job is to take those 6 cryptic latent vectors from the student and translate them back into the teacher's natural language.
Ah, I see.
And they train this with a loss function that's a lot like DPO, direct preference optimization. They look at all the teacher's plans, figure out which ones led to success and which ones failed.
The good traces and the bad traces.
Exactly. And they train the student so that its latent vectors, when you run them through the verbalizer, decode into the good reasoning and not the bad.
That's incredibly smart. So the student has to learn a compressed representation that could be unpacked into good English, even though it doesn't actually do the unpacking at runtime.
You got it. It learns a dense shorthand. It's like it's learning the concept without needing the words.
Okay, but robotics isn't just about concepts. It's about geometry. It's about where, not just why. How does it handle the spatial part of the plan?
That's the other half of the architecture. They call it action-aligned visual plan distillation. As the student is generating those 6 reasoning vectors, it's also, in parallel, generating a set of spatial tokens.
In parallel, so at the same time.
Yes, concurrently. These are just learnable tokens that pay attention to the visual input. Then an MLP projects the hidden states from those tokens to predict 2D waypoints right on top of the image.
I saw that in the paper. It looks like a series of green dots appearing on the object the robot's about to grab.
That's the one. That's the visual plan. And they train the student to make its green dots line up with the teacher's green dots. So it's compressing both the why, the latent reasoning, and the where, the spatial plan.
Okay, so we have the compressed thought and the visual map.
Yeah.
How did that translate into actual motor commands? You still have to drive the robot arm.
Right, so they don't have the VLM output actions directly. They feed this compressed plan into a separate action model, in this case, a diffusion transformer like RDT.
Which are pretty much the standard for smooth, robust control these days.
They are, and the really innovative part is how they connect them. They literally pull the key value cache from those spatial tokens in the student VLM.
The KB cache. That's just the transformer's internal memory, isn't it?
It is, but it contains this super rich, condensed representation of the entire plan, the reasoning and the visual targets all mixed together. They take that cache and feed it directly into the diffusion policy as a condition.
So the action model is basically listening to the VLM's thoughts.
That's a great way to put it, and it's very efficient.
Yeah.
During this phase, they freeze the giant VLM and the vision encoder. They're only fine-tuning the much smaller action model.
It's a modular design. You've got a frozen brain, the VLM, and you're just training the nervous system, the action model, to understand its signals.
Exactly, and that makes it much more practical to train and iterate on.
All right, let's get to the results. The architecture sounds great, but does it actually work? We mentioned the 89% latency drop. In raw numbers, what does that mean?
Well, if you compare their 3 billion parameter Fast-ThinkAct model to the 7 billion parameter ThinkAct teacher, they cut over 5,600 milliseconds per step.
5.5 seconds. That's the difference between a robot that's actually useful and one that's just a lab demo.
It's night and day. And even for same model size, the 3B Fast-ThinkAct is about 7 times faster than the 3B ThinkAct. It's just no contest.
But usually with distillation, you take a hit on performance, right?
Yeah.
The student is never quite as good as the teacher.
That's what you'd expect. But this is where the results get really interesting. On a bunch of benchmarks like SimplerEnv and LIBERO, the Fast-ThinkAct student actually did better than the teacher it learned from.
It beat the teacher. How is that possible?
The theory is that forcing the teacher to generate explicit text actually introduces a kind of noise. You know, a VLM can get distracted, hallucinate details, get bogged down in grammar that has nothing to do with the physics of the task.
The latent space cuts out all that fluff.
It's all signal, no noise. It's optimized purely for the task reward, not for linguistic elegance.
And that really showed up on the bimanual tasks, right? The RoboTwin benchmark.
Oh, yeah. 2-arm coordination is incredibly difficult. And Fast-ThinkAct just blew past the baselines like RDT and $all, especially on the long horizon tasks.
Which really proves the reasoning component is working. It's maintaining a coherent plan over many steps.
Absolutely. And the ultimate test of that was in the failure recovery experiments, the RoboFac benchmark.
This is where they start messing with the robot, like knocking a block out of its hand.
Exactly. A normal imitation policy is brittle. It drops the block and then just keeps going through the motions like it's still holding it.
Just mindless execution.
Right. But Fast-ThinkAct, it notices. It detects the failure. And because of the verbalizer, we can actually decode its thought process as it corrects itself.
What did it think?
In one of the examples, the robot drops a block and the latent state shifts. You run that new state through the verbalizer, and the output is something like move backward and realign.
And it did that. It actually executed the recovery plan.
It backed up, centered itself over the block again, and regressed successfully.
That is huge. That's true autonomy. Not just following a script, but adapting when things go wrong.
It's that blend of reactive speed to catch the error and reasoning depth to figure out the fix.
I'm going to go back to the verbalizable idea for a second.
Yeah.
We know it helps with training, but is it useful after the model is deployed? Or is it just, left behind.
Oh, it's critical. It's critical for interpretability for the whole black box problem.
Right.
If your robot drives into a wall, you need to know why. With a normal model, all you have is a bunch of weights. You can't ask it what it was trying to do.
You can't ask a vector, what were you thinking?
But with this, you can. You can take the latent vectors from that moment, plug them back into the verbalizer during a postmortem, and get a plan in English. If it says, I'm driving through the open door, but the door was closed, you know you have a perception failure.
As opposed to, I am testing the structural integrity of the wall.
Exactly. One is a bug, the other is something much scarier. The verbalizer is our window into the machine's intent.
That brings a fascinating question, though, a provocative thought. The model is trying to do two things, right? Satisfy the verbalizer by creating vectors that map to English, and satisfy the policy by succeeding at the task.
Linguistic alignment versus physical success. A dual objective.
Right. Now, what happens when we give it tasks that are incredibly complex, physically? Things that human language is really bad at describing, like the fluid dynamics of pouring a liquid or the friction coefficients of a slippery object.
That's a really good point. English is clumsy for physics.
So is it possible that the model will eventually discover latent representations that are perfect for solving the physics, but are basically untranslatable? That it starts to cheat on the verbalizer because a correct thought is actually gibberish in English?
I think you're describing the emergence of a native robotese.
Robotese.
Yeah, a language of thought optimized purely for physics and control, not for human communication. Right now, we're forcing it to think in ways that are legible to us. But the most efficient way to compensate for angular momentum during slip might be a vector that just looks like noise if you decode it.
So we might face a choice down the line. Do we want robots we can understand? Or do we want robots with superhuman physical intuition?
That might be the ultimate trade-off. If we cut that verbalizer tether completely, we might unlock a new level of performance, but it would be a true black box, a robot that could, catch a fly with chopsticks, and we would have absolutely no idea how.
It's an exciting and slightly unnerving thought. Just to wrap up, it seems like the big takeaway here is moving the computational costs of thinking from inference time to training time.
That's it. That's the correct engineering trade-off for real-world robotics. Fast-ThinkAct feels like the system 1.5 we've been needing for a long time.
If you want to see this in action, the project page has some great videos of the failure recovery and the visualizations of the spatial tokens, those green dots.
Yeah, they're definitely worth a look. It makes the whole concept click instantly.
That's a wrap for this episode of AI Paper Podcasts. Thanks for tuning in, and we'll catch you on the next deep dive into the ARCs.